Welcome to the next lecture in electric circuit analysis. The tutorial problem we are going to solve here is on single phase AC power. The first problem, we have to determine the power factor of the circuit as seen by the source. So in this circuit, we have to determine what is the power factor which is seen by the source. Second, what is the average power which is delivered by the source. So the source is 30 angle 0 volt RMS. So this is a voltage source and it is given in RMS quantity. Usually AC source always will be given in RMS quantity and it is represented in the form of a phasor. So phasor means you will be having a magnitude as well as angle of the source. The elements comprise of a resistor, a capacitor and another resistor. We have to note that all the elements should have the units in ohms. So here the capacitor unit is in ohms. If it is in farad, then we have to convert that in ohms using the concept of the capacitive reactance is equal to 1 by omega c. So given the frequency of the system, we have to obtain the capacitive reactance in ohms. Similarly, for inductive reactance XL, we have omega into L. So depending upon the frequency omega, we can convert the Henry into ohms. So whatever may be the network, we have to convert each element in ohms and then only we have to start the calculation. Here we need not to worry because the elements are in ohms only. So in order to determine the power factor of the circuit, we will start with the total impedance which is seen by the source. So can we replace this entire network with one impedance which is Z or the total equivalent impedance of the network? We can see that 4 ohms and the capacitive reactance are in parallel, which is in series with the resistance 6 ohms. So we can use the concept of parallel series combination to get the equivalent impedance as seen from the source. So which is equal to 7 angle minus 13.24 degrees in ohms. So that gives the total impedance which is seen by the source. Now the power factor is nothing but the cosine of the angle between the voltage and the current. So the angle between the voltage and the current can be obtained from the impedance angle. So impedance angle is 13.24 with a negative sign, which is representing that the element is basically a combination of RC network. So here we have negative sign which can be included in the cosine because the power factor is leading where the current will be leading the voltage by certain angle which is 13.24 which is 0.9734. Usually we know that the power factor value will lie between 0 to 1. So the maximum value of power factor can be 1 which is for the resistive network. So here since it is a capacitive network, we are having a leading power factor and the value is 0.9734. Next, we have to determine the RMS value of the current. So the RMS value of the current in accordance with the Ohm's law is the voltage divided by the impedance. The voltage is given as 30 angle 0 and the total impedance of the network we have calculated as 7 angle minus 13.24. So we can divide the voltage with the impedance which gives the current to be 4.286 angle 13.24. So this is the current which is originating from the source. So this is the RMS current which is originating from the voltage source. We have to determine the average power. So the formula for average power is the product of the RMS voltage into RMS current multiplied with the power factor of the system. Here the RMS voltage is 30, RMS current magnitude is 4.286 and the power factor is 0.974 which gives 125 watt as the average power which is supplied by the source. The same quantity we can determine by some other method or where the power can be determined directly from the current, that is I RMS square into R. What is R? R is the resistance of the impedance part. So if we say the impedance is basically a complex quantity which is having a resistive part or the real part plus J times some reactive part. Now here the real part, which is the resistance, can be substituted here to determine the power, because power is what we observed in the network. So the net power which is absorbed in the network is basically 125 watt, which is similar to what we have got by the previous formula, that is Vrms IRMS into power factor. The next problem, we will be having the voltage, which is the instantaneous voltage equation of the load as 60 cos omega t minus 10 degree volt. So this is the representation in the time domain. So when we represent in the phasor domain, it will be having the frequency term. Here we are having the time domain. And the current through the element in the direction of the voltage source is given to be 1.5 cos of omega t plus 50 degree. So both voltage and current are given in the instantaneous form, which is a function of time t. So any voltage and current which is given in the function of time t is known as instantaneous voltage and instantaneous current. Find the complex and the apparent powers, the real and the reactive powers, the power factor and the load impedance. So this is what we have to determine from this problem. Now the voltage and the current equation are given, which is the instantaneous voltage and instantaneous current. We can convert that into RMS quantities or the root mean square quantities. So the maximum value of the voltage is 60. So if I divide the maximum voltage by root 2, I'll get the magnitude of the RMS voltage. Now the angle is minus 10 degree, which we can directly take it minus 10 degree. So this is the phasor representation of the RMS voltage. Similarly, the maximum value of the current in the RMS is 1.5, which we can divide with root 2 to get the maximum value of the current IRMS, and the angle is plus 50 degree. So both Vrms and IRMS, we have converted that in phasor quantity. So the complex power formula is Vrms into IRMS conjugate. So we have a conjugate here, which means that the sign of the angle of the current will be reverse. So we will be putting the value of Vrms into IRMS. Now the sign is reverse for IRMS conjugate. We are getting 45 angle minus 60 degree, and the unit is in volt ampere. So the complex power as unit is in volt ampere. Now once we have got the complex power, the apparent power is nothing but the absolute value or the magnitude of the complex power, which is 45 volt ampere. If we represent this complex power in the form of the rectangular form, so we have 45 cos of minus 60 plus j times sine of minus 60, which gives to be 22.5 minus j 38.96. The real part of this complex power is P, which is the active power, and the reactive part is nothing but the imaginary part of the complex power. So we can say that the real power or the average power is 22.5 watt, and the reactive power is minus of 38.97 volt ampere reactive. So note the unit. The unit of complex power is volt ampere, the unit of real power is watt, and the unit of the reactive power is volt ampere reactive. Now the negative sign indicates of the reactive power that the load is capacitive in nature. So when the reactive power will be negative, in that case we will understand that load is capacitive because the current is leading the voltage by certain angle, which is the impedance angle. The power factor can be determined as the cosine of the angle between the voltage and the current. So here we can see that the angle is 60 degree in the complex power, then we can take minus 60 degree, so it is 0.5 leading, and the negative is coming because it is a capacitive load. Finally, the load impedance can be determined as from the Ohm's law, the ratio of the voltage by current, and these two are in RMS phasor quantity. we can put the values of voltage and the current, we'll get the load impedance. So you can note here that the angle of the load impedance is minus 60 degree, which is the angle between voltage and current. The same angle you can get it from the complex power also. So either from the complex power you can get the power factor angle, or from the load impedance you can get the power factor angle. Problem number 3. A load Z draws 12 kVA at a power factor of 0.856 lagging from a 120 volt RMS sinusoidal source. Now note here that the power which is given is in kVA, which means the complex power is given. The voltage which is given is always will be given in the form of RMS voltage. Calculate the average and the reactive power which is delivered to the load, the peak current and the load impedance. So these are the data which we have to calculate for the problem number 3. Let us see the solution. So the power factor is given to be 0.856, which will give us the angle between the voltage and the current theta using the concept of cos inverse of 0.856, which theta is equal to 31.13 degree. Now the complex power is given to be 12 kVA, which is 12,000 volt ampere. Hence the real power and the reactive power we can determine from the complex power S of cos theta and S of sin theta. This is in accordance with the right angle triangle rule. So if we have a right angle triangle, then the hypotenuse represent the complex power, and the angle, this one, is the theta, which is the power factor angle. So the real power is represented by the base, and the height represent the reactive power. So S cos theta represent the real power, and S sin theta represent the reactive power. So we can substitute the values of the complex power, the power factor, and the sin theta value, will get the real power and the reactive power. The real power unit will be in kilowatt, the reactive power unit will be in kVAr. So the total complex power is nothing but P plus JQ. So the real part is the real power, and the imaginary part is the reactive power. So here the unit will be in kVAr, reactive. So we can determine the current conjugate from the formula that we know that the complex power S is nothing but the RMS voltage multiplied with the conjugate of the RMS current. So RMS current conjugate we can easily compute from the complex power divided by VRMS, which gives us to be 100 angle 31.13. So the maximum value of the current is nothing but the root 2 multiplied with the RMS value, which gives to be 141.4 ampere. Then the impedance is nothing but VRMS by IRMS, which gives to be 1.2 angle 31.13 milliamps. Next problem. Now this problem is based on conservation of AC power. So here we can see one circuit where a load is there which is operating at 12 kilowatt and 0.8 power factor lagging. So this is the load which is represented by 20 kilowatt 0.8 power factor lagging, and the voltage which is there across the load is given to be 220 angle 0 volt RMS at a certain frequency which is 60 Hz. The impedance of the line, so this is what the line is there through which the power is being transferred. So the line impedance is 0.09 plus J times 0.3. We have to determine the voltage and the power factor at the input of the line. So here the input or the source is there, which we have to determine what is its voltage and what is the power factor at the input of the line. So first we need to determine what is the complex power. So the complex power we can determine as the real power divided by the power factor cos theta, because the power of the load is given in kilowatt. The meaning is it is given the real power. If it is given in kVA, then we can take that to be the complex power S. But here the real power is given, so we can use P by cos theta, which is P by power factor. Hence it gives to be 25 kVA as the complex power which is given to the load. So the load kVA rating will be equal to 25 kVA magnitude and the angle will be 36.87, which is nothing but the power factor cos phi. So here the cos phi value is 0.8. So I can determine from here the phi is nothing but cos inverse of 0.8. So cos inverse of 0.8 is 36.87. So I'll get the real part as the real power and the imaginary part as the reactive power, because the complex power is given by P plus J times Q, that is the real power and the reactive power. Now the current is nothing but the ratio of the complex power and the voltage conjugate. So the complex power we have obtained as 25 kV angle 36.87. The voltage of the load is given 220 angle 0. Conjugate we have to take it because of the current. So it gives to be 113.64 angle minus 36.87, and that is also the RMS current. We have to compute the complex power of the line, which is nothing but the current which is flowing in the line square multiplied with the line impedance. So line impedance is given here. Current we have computed, the magnitude is 113.64. So that gives us the power of the line. Similarly, we can determine from the conservation of power, the total source power will be the power which is consumed at the load plus the line power. So this is in accordance with conservation of AC power. So we get 28,356.25 angle 41.73 volt ampere. So the source voltage we can get as the apparent power of the source, which is the magnitude of this complex power divided by the line current, which is given to be 249.53 volt RMS. So this is the voltage of the source, and the power factor is nothing but the cosine of the angle of the complex power, which is equal to 41.73. That gives to be 0.75 lagging as the power factor. Note, we could have solved this problem alternatively by using the concept of KVL also. How? Let us see. So first we have to compute the current, because this is only one loop problem where we have the source voltage. This is what we have, the line impedance. Then we have the impedance of the source, impedance of the load, and then this is the circuit. So the current which is flowing here is IN. So the current we can determine, voltage of the line we can determine from the concept of total impedance multiplied with the current. We'll get the line impedance and the source impedance using the concept of Kirchhoff's voltage law. So the voltage across the line plus the voltage across the load will be voltage across the source. That is what we have done it. And the angle between the voltage and the current, which is the power factor angle, we can compute it, and hence the power factor will be 0.75, which is cosine of the angle between the voltage and the current, and is 41.73. So we can compute these by this method also using the concept of KVL, or we can get it from the power formula. Next problem, there is a series connected load which is drawing a current. Instantaneous current equation is given, and the voltage across the load is also given. Find the apparent power and the power factor of the load. Determine the element values that form the series connected load. It is not given that what type of load it is that is making the series connected load, that we have to determine. So the solution starts from the instantaneous current and the instantaneous voltage that is given in the problem. We need to determine first the complex power, which is the product of Vrms, Irms. So here the maximum value of the current and the maximum value of the voltage is already available. So we can divide that with the root 2 to get the RMS voltage and the current, and multiplied with that will give you the apparent power, which is 240 volt ampere. This is nothing but the magnitude of the complex power. So the power factor is cosine of the angle difference between the voltage and the current, which is total we get minus 30 degree, which is 0.866, and it's leading. The reason is we are having cos of minus theta. So minus indicate that the net power factor is leading in nature. So obviously it will be capacitive load will be there. Same thing we can obtain alternatively from the impedance as the ratio of the voltage by the current. which is 30 angle minus 30. So here minus indicate that it is capacitive, and 30 degree indicates that the angle between voltage and current is 30 degree. So the impedance, if we obtain in the rectangular form, the real part will be the resistance and the imaginary part will be the capacitive reactance. And here we can see that 30 angle minus 30, the real part is 25.98, which is the resistance of the load. Power factor, again we are getting cos of minus 30, which is 0.866, leading in nature. Now the load is basically a resistor and a capacitor in series. The resistor value we have already calculated, 25.98. What is the value of this capacitor? So first we need to determine what is capacitive reactance. Capacitive reactance, we can get it from the imaginary value of the impedance, which is equal to minus 15. So this is equal to 1 by omega c, and we can find out what is the capacitance of the system, where omega is the frequency which can we get it from the instantaneous current or the instantaneous voltage equation, which is equal to 100 pi. So the capacitor is 212.2 microfarad, which is a series combination of resistor and capacitive load. Next problem. So there are three complex power, S1, S2 and S3, which are given in parallel connected load from a source 240 volt RMS 50 Hz. We have to determine the total complex power and the input power factor. So what is the total complex power of these three load, and what is the input power factor of this source? We can use the concept of current division in the three parallel loads I1, I2, I3, and the net current will be drawn as I. So we can apply the Kirchhoff's current law as the total current is equal to I1 plus I2 plus I3, and the current flowing here we can easily determine from the voltage and the complex power S. So the current 1 we can determine as voltage divided by the complex power. Similarly I2 and I3 we can add and find the total current. But we know that the complex power S is nothing but VI conjugate. So it is the conjugate of the current that we required. So we can find the conjugate of the current by changing this sign. So the total complex power now we can get at VI conjugate, because V is already given to us, I conjugate we have determined. So this is the complex power of the entire system. Problem number 7 is based on maximum power transfer theorem for the AC circuit. So here is the circuit which is given to us. We have to determine the value of the load resistor RL. So what is this load resistor RL? That will absorb the maximum average power and calculate that power. So here in the network we see there is a resistor, there is a capacitor, and there is an inductor. So this is an RLC network with a source voltage. What is this value of the resistor? So this is from maximum power transfer theorem in AC network. If you remember, in DC we have discussed that from the maximum power transfer theorem, that when the load resistor will be equal to the Thevenin resistance, then the maximum power will be transferred. So in DC we don't have inductors and capacitors, but in AC we will have inductors and capacitors. So this formula will be little bit changing, where the load impedance will be equal to the conjugate of the Thevenin impedance. So little bit changes is there in the AC network. Let us see how to calculate. So first we need to obtain the Thevenin impedance of the network. So we have to remove this load resistor and make it open circuit. We have to find out what is the Thevenin equivalent of this by short circuiting this voltage source. So we can use the concept of series parallel impedance, which comes to be 9.412 and plus J 22.35 ohms. Now the voltage of the Thevenin, which is nothing but what is the open circuit voltage at the load terminal. So we can use the voltage division rule, and we can find out that 72.76 angle 134 volt is the Thevenin's voltage. This we have discussed very in detail in the previous lectures, where voltage division we have studied. So here we have seen that the Thevenin impedance, the real part is basically the resistance Thevenin, and the imaginary part is basically the reactance Thevenin. So the real part is giving to be 9.412 and imaginary part is 22.35. So the resistance of the load has to be equal to the magnitude of the Thevenin impedance, which gives to be 24.25 ohms, because under root of real part plus imaginary part, which is 25.25 as the Thevenin impedance. And in accordance with the maximum power transfer theorem, the load impedance has to be equal to the Thevenin magnitude. And hence, the current which is flowing will be equal to V Thevenin by Z Thevenin plus RL, because our network will be now in this way. So here we have V Thevenin, then we have the Z Thevenin, and here we are having the value of RL. What is RL? So the total current which is flowing here is V Thevenin by Z Thevenin plus RL, which gives to be 1.8 angle 100.42. Now, the power maximum is equal to half of the current square multiplied with the load resistor. Current magnitude we are taking, so that gives to be 39.29 watt as the maximum power which is being transferred. So we have to determine what is the value of RL. So the value of RL is 24.25, and what is the maximum power that can be transferred, that is 39.29 watt. This is the last problem of this tutorial, where we have two loads Z1 and Z2. Its values are given 60 angle minus 30 and 40 angle 45, and there is a source 120 angle 10 which is delivering these two loads Z1 and Z2. We have to determine the apparent power, real power, reactive power, or power factor which is supplied by the source and seen by the source. So we can use the concept of current division because it is a parallel load. Hence, the current I1 and I2 we can determine from the voltage V divided by Z1 and voltage V divided by Z2, because the voltage will be remaining same in parallel network. So 2 angle 40 and 3 angle minus 35, we are getting the values of the current in the two impedances Z1 and Z2, and hence the load impedances S1 and S2 in the values of Z1 and Z2 we can get it from the VRMS square divided by Z1 conjugate formula. So that gives to be the impedance of the load S1 and S2 both in the polar as well as in the rectangular form. So this is the polar form and this is the rectangular form. So the total impedance is the summation of the impedance, the total complex power is the summation of the complex power of the load 1 plus load 2. We can add it. And the apparent power is nothing but the magnitude of the complex power, which is under root of real square plus imaginary square, which gives to be 48.6 volt ampere as the apparent power. The real and the reactive can be obtained from the total power concept. The complex power is equal to the real part plus J times the reactive part. So the real part of the complex power is 462.4 and the imaginary part is 134.6 volt ampere reactive. So this is the total power, real power of the two loads and the total reactive power of the two loads. Power factor we can get it from the ratio of the real power divided by complex power. So total real power by total complex power or the apparent power, we will be getting the power factor which is equal to 0.96. Since it is positive, so it is lagging in nature. We can verify this complex power of the source by using the concept of the current, that is I1 plus I2 is the total current, and the source power is BI conjugate. So total current we have computed as 4.024 angle 6.21. We can take the conjugate of that, so negative will be positive, multiplied with the total voltage which is 120 angle 10. That gives to be 463 plus J 135 volt ampere. So this is what we are getting it at the same when UV is the concept of the complex power. So this verified that yes, the answer is correct. So this complete the tutorial problem on single phase AC power. We'll discuss the power conservation, and we will also discuss how the power factor correction is done and the three-phase AC power is being calculated. So see you in the next tutorial. Thank you for now.